are you going to buzz us on your YouTube channel?
Yes.
I'll subscribe.
Yeah, I'll subscribe to that.
All right, there we go.
Remember when we differentiated, there was those rules that we had? And remember, those aren't all the rules, but those are the ones that we are concerned with because those are the big ones that come up more often. And one of them was if we had a constant. So if we were to take the derivative of a constant, what does that give us?
0.
0. So that one's very easy. Well, the problem is, it's easy to differentiate, but when we anti-differentiate, it gets a little more complicated. Because if something's 0, it can be anything. It can be up to infinity. But we still gotta account for it.
Initial condition.
Yeah, that's where that comes in.
Bless you.
Okay, so when we take the derivative of a constant, it gives us 0, so the constants will be lost when you take a derivative. So for example, if we were to have these two equations, xt equals 2t plus 1 and xt equals 2t minus 1, the derivatives are the same. Well, how do we know which constant to put on to the function when we anti-differentiate? That's where it gets a little confusing. It's easy to differentiate, but when we try and go backwards, now it's like, well, which one was it? Positive or negative? They both give us the same answer, but they're completely different functions. So we have a very complicated physicsy way of adding this constant or figuring out what it is. Yes, very technical.
Plus 1. Oh.
I wonder if it's 2. I wonder if it's 6.
Or if
Plus
it's
C.
750,000.
So those who've already been through calculus, yes, you usually would just say plus C. But when in physics, what does anybody know what C represents?
Calculus.
Plus calculus.
Yeah, I'll give you that. Well, I'm talking about like X is for position, V is velocity. What would C represent?
The speed of light.
It's speed of light. Well, I mean, do we really want to deal with speed of light when we're talking about a projectile? Like right now, and we don't want to deal with that. So we still got to use that constant somehow. And you guys already actually know what to put. We slap a constant on it. It's basically our very complicated way of doing it. So for example, if our antiderivative gives us our position, well, it's going to be, the constant will be initial position. So if you're used to already putting a C for a constant, all you're doing is putting in x0. If you are anti-deriving to get your velocity function, it would be v0. Same thing for acceleration, you'd be acceleration, a0. You just slap it on the end. Now we can actually solve for this variable and figure out what value it should be. But to do that, we may need some additional information. So then this is what we call initial conditions. So this information must be provided in the problem if we're expected to anti-differentiate. So if it just wants you to come up with a function, leave it as the variable. If it wants you to actually solve for everything in that function, then we may need additional information. A lot of times it's not very complicated to do because it'll be like when time equals 0, well, plug in 0 for time. And there's your initial position. Done. So it's mostly just going to be plug and shove once you actually have the equation. Or the rest of the equation, I should say. So if we have a derivative in the form of something like this, so basically subscript or coefficient x to the n, then we can find the antiderivative by undoing the power rule. So we know for the power rule, we would bring down that n, subtract 1 from that power, and that's the power rule. Now we're just going to basically go backwards. Okay, so the antiderivative of that, normally we would multiply the n by the a, and then subtract 1 from the n. So the easy part, now we're going to add 1 to the n. It's the opposite. And then instead of multiplying the n and the a, now we're going to divide the n plus 1 by the a. And we still have that constant there, which I'm just writing out as constant right now. Yes, I do have x in here, so we could assume position. But I have an example coming up. You could just kind of think of it as you do the opposite of whatever you do to differentiate. So you've already done the power rule, you just go backwards and slap a constant. So here's an example. Find an expression for the position of a particle whose velocity is given by vt equals 2t if it was at x equals 3 at a time of 2 seconds. So we know where it is at 2 seconds. But we want to find what the position function is when we're given just the velocity function. So our velocity function is 2t. So first, we want to anti-differentiate that. If we anti-differentiate, that will give us our position function. So what we're going to do is to get that position function, we're just going to do the power rule but backwards. So it's 2t, and that is t to the what power? 1. So we would get 2 over 1 plus 1 times t to the 1 plus 1. Since we're going to position, we slap a constant, x naught. So now when we simplify this, we should just get xt equals t squared plus x naught. So there's our position function. But we want to know what x naught is as well here. And we have extra information that'll let us actually solve that. We know that at x equal, it's at position 3 at 2 seconds. So we want to find that x naught. Oops, I forgot I had one coming. Anyway, so we're going to plug in that 2 seconds for our time. And when you plug that in, we get 3. We already know it should be at 3. Plug those in, solve for x naught. When we solve for x naught, we get -1. So that means the initial position was at -1. And now we can substitute that into our equation we just got to get our final position function. So we would get t squared minus 1 is our position function. Any questions on that? So just do the power rule backwards, slap that constant on, and then solve for the constant. Not too bad, right? Yes, too bad. A lot of too much work. Now we call this anti-derivatives. Well, another way we could say this is, because I know, oh, you know what? Chris.
Integral?
It's an integral. That's another way to say it. And so that's where we get the integral sign. Get this fancy, kind of looks like a fortissimo. No, it's more like a forte.
Yeah.
Fortissimo has the circle in it, doesn't it?
Fortissimo is 2 F's.
Yeah, it's just 2 F's.
2 F's. Why am I thinking there's, which one is it with the circle in the middle?
The whole note?
Oh, treble clef?
No, that's not treble clef. Treble clef is more fancy. Because that's what I used to play was treble clef, so that's all I remember. Anyway,
Breaking the dance.
What did you play?
alto sax. They kept wanting me to play baritone, but I'm like, no, I'm not dealing with that. So sometimes you'll see a function that looks something like this. So this is saying x equals the antiderivative of v. So our position function is equal to the antiderivative of the velocity function. So it's a lot easier, a lot smaller to write something like this using the integral sign. So the meaning of the symbol, and you're going to go more in depth into this in calculus if you already haven't been through Calc AB. But basically think of the symbol as a stretched out S for sum. It is a very small displacement. Basically it's an infinitely short time interval. And we're just adding all these very, very tiny portions together to figure out what that displacement is between the initial and the final positions. So dx would basically be all these little pieces. And then if we take the sum of all those dx's, that'll give us our change in position. But remember, we do this because it'll be a curved graph. And so we try and break it down into very, very small chunks so that it's basically very, very, as straight as we can get it to be for like straight lines. Because that's a lot easier to deal with. so here's an example. We have an object that started at position x equals 0 at t equals 0 and moved according to the following expression. Vt equals 12 minus 2t to the 2t cubed. Okay. What was the object's position at 4 seconds? So the first thing we need to do is find that position function. Okay. So to find a position function from the velocity function, we take the integral of it, or the antiderivative. So we're going to take the integral of that 12 minus 2t cubed. So we're going to do the reverse of the power rule. Well, that 12, it's as if it has the t next to it, but t to the 0. Because anything to the 0 power is what? 1. So the t is technically there as if it was t to the 0. And you remember when we anti-differentiate, we're going to add 1 to that power. And so 0 plus 1 down here, t to the 0 plus 1, plus, and we have the negative 2 here, and t to the third, so it'd be 3 plus 1, and then t 3 plus 1, and then we're finding the position function, so we slap the constant on. So x naught. So we solve that and simplify it. We end up with this function, and we know that when t equals 0, our position is 0. So what can we say about that constant?
0.
It will be 0. Because if we were to plug in 0 here for time to get 0 as our answer, well, that has to be 0. So our function is going to be 12t minus 1/2 t to the 4th. Now we want to know what the object's position is at 4 seconds. So what do you think we need to do? Just plug it in. Super easy. So we have our function, plug in the 4, and no, not 16. Negative 8. So it'll be at a position of negative 8. Any questions on that? Let's look at another one. Here we have an object that's set at rest. At time t equals 0, moved according to the following. At equals 5. What's the object's velocity at 3 seconds? So here we have the acceleration function. We want to know what the velocity is. So we still do what?
Integral.
We take the integral. Well, our function is just at equals 5. So basically we're taking the integral of 5 with respect to t, officially we could say it. And so it's like we had a t to the 0 next to that 5. So once again, we would get 5 over 0 plus 1 times t to the 0 plus 1, and then slap the constant on. And in this case, we're talking about velocity function, so it would be v naught. So 5 over 1 times t plus v naught. We want to know what's the object's velocity at 3 seconds. Plug in that 3 seconds. Or, well, let me say this. What is our initial velocity?
0.
0, because it says at time t equals 0, it's 0. So the v naught actually goes away. So we just actually have vt equals 5t. So now we're going to plug in that 3 seconds. And what is that velocity at 3 seconds? 15. Any questions there? one more, guys. So here we have an object that's moved with an acceleration that varied with time according to at equals 3t. So we have our acceleration function. What was the object's position at time equals 4 seconds? If the object was at rest at 2 seconds at a position of 8 meters. Well, if we have the acceleration function, we want to know the position. What do we need to do?
Anti-differentiate twice.
Anti-differentiate twice. So we got to go to the velocity function and then go to the position function. So let's go to the velocity function first. So we're going to integrate 3t with respect to t. And once again, reverse power rule. So 3 over 1 plus 1 times t to the 1 plus 1. Slap that constant on. So v naught. And we can simplify. But we want to find what that v naught is. We know that at 2 seconds, it was at rest. It tells us it was at rest. So we can plug in those values and figure out what that v naught is. And so we get a v naught of -6. We get our final velocity function. Once we have that velocity function, now we just take the we take the antiderivative of that and repeat to find our position function. Now it gets a little more complicated because we have that 3 seconds in there, but we still do everything the exact same. It just seems like it gets a little bit longer because of that. And then we also know that it was at rest at time t equals 2 seconds at position 8 meters. So then we can find our x naught by plugging that value in there. So at 2 seconds it's at 8 meters. Plug those in to solve for x naught, and we get a final position function of 1/2 t cubed minus 6t plus 16. So there's our position function. But we're not done yet. We still got one more thing to do. We need to figure out what was the position at 4 seconds. So now we just need to plug in 4 for time and solve for our position. Plug in 4 for time. We get a final position of 24 meters. So this would be kind of the most complicated you would get in this unit.
Fairly straightforward. Fairly straightforward.
Any questions on that, guys? Okay, so I do have a practice for you guys that'll be in OneNote. I'm gonna double check because I don't know if it went through earlier, so I'm gonna double check. And then I'll post the key for the derivative practice from when I left. And tomorrow we'll do a mixed practice, Thursday review, and Friday's test. So technically we've covered everything in this unit. All it's gonna be is one-dimensional motion, and then the only calculus on here is going to be going between the functions and solving like we did here. So this would be like the most complicated that could be on the test. I want you to do a few examples. It's not bad. Just reverse power rule. Yeah. Okay.
Is there a practice today?
Yes. I'm gonna double check to see if it actually went through or
Is it
not.
on its learning or what?
It will be